Okay, so the main topic of this lecture is going to be the most famous entangled state for qubits, which is a 2-qubit state, which goes by several names, but we're going to call it by this name, EPR. And I decided that for us in this class, we're going to let this stand for this state, 0, 0 plus 1, 1. Now this is an unnormalized state, and last time I wrote the normalized form of it. In the normalized form of it, you have to put square root of half factors on both these, but you know my feeling about square root of half, I don't like it, so I just decided we're going to make this the official definition, and be cool with the fact that it's unnormalized. Next class I'll tell you why. Again, it's called EPR. It stands for Einstein, Podolsky, and Rosen, because they imagined an experiment that we're going to talk about next class, which is an experiment is just some code, that really mystified them using this particular state, and it upset them, but it was legit. But we'll explain that next time. And if you don't like that, you can maybe try to think that it stands for entangled pair. I don't know, that's my best mnemonic for it. Okay, so this is a very important 2-qubit state. We'll see why. Let's just see how Alice and Bob can get it. It's very easy to prepare. So I'll write like a little bit of code here. I'll call make EPR. I hope you could all figure out this code. So from scratch, we'll do new qubit A. And then we'll do add and diff on A. Okay. Normally people would write Hadamard here, but that would get your square root of halves in, and you'll get the normalized version. Because we like the unnormalized version, we'll do add and diff. And then we'll make another qubit called B. Of course, we need 2 qubits here. And the final operation will be if A, then toggle B. Okay, so this is 4 simple lines of code, and I claim that after you run this code, the joint state of A and B is exactly EPR. So let's just check that. Okay, after new qubit A, of course we have 1 qubit, and it's just 0. What about when you do add and diff on A? Well, you get the ket plus unnormalized, or you could say, oh, we have like 1 amplitude on 0 and 0 amplitude on 1. So the new amplitude on 0 is the add of these 2 things, which is 1. And the new amplitude on 1 is the difference of these things, which is also 1. So we get to just ket 0 plus ket 1. Okay, then we bring in a new qubit B. So of course that just sticks like a B, which is always 0, into the second slot. Okay, so it's always, I'll emphasize this today. It's always like the first qubit is A and the second qubit is B. Okay, and finally we do if A, then toggle B. So what happens here? Here A is not true, so we don't do anything to B. Here A is 1, so we do toggle B. And so voila, we get to the EPR state. Okay, now let's just take a little look at this code again. From this, mental perspective of Alice and Bob physically operating on like a physical object. And one thing you can notice is that like up until line 3, Alice and Bob could be in separate rooms. So like here's the instructions for the experiment. Alice, who owns A, she like makes a new qubit A in her own office. And then she can do this operation on A herself. Meanwhile, Bob in his own office can do new qubit B. So up to line 3, these could have come before 3, or 3 could have come first, or 3 could have been between 1 and 2. That can all happen separately. But this operation is like the joint operation on A and B. And like really to achieve this, like you have to physically bring these like objects together and like do some physical operation on these 2 qubits together. Okay, so for line 4, they really have to get together in order to do this final operation. And we kind of know that because like otherwise, if they never get together, their joint state will be unentangled. It'll be in this like factorized form, the state of A, tensor product, the state of B. But we saw last time, this is not unentangled, it's entangled. But just for, the mental excitement of it all, you should imagine like maybe step 5, Alice and Bob like depart from each other. and they keep the qubits that they owned. So this is possible if they're careful. They put their qubit in like a special fridge and like don't touch it, and it stays out of the light and so forth. Alice can walk away holding A, and Bob can walk away holding B, and then they can be in their own labs far apart from each other. One person on CMU, one person at Pitt, and they're still in this state if they're careful about it. Okay, so they can maintain their entanglement despite being far away. In fact, for this party trick that we're about to do, which is quantum teleportation, they've done this physically, like with actual experiments, many times. And it exactly starts with this setup. And like the most famous one early on for doing this, they did it in the Canary Islands. I think the Canary Islands. Is one of the Canary Islands Tenerife, another one something? Anyway, I think they did it in Canary Islands, two like islands in the Atlantic. And literally like they had like one qubit on the one island and the other qubit on the other island. Apparently they did it there because like they have like nice telescopes there, and like they were using photons, which is light. Okay. And then most recently, like a few years ago, this famous quantum computer scientist engineer, Pan, his group in China did this quantum teleportation experiment where one qubit was like on this mountain in Tibet, and the other one was on a satellite in space. So there's like, 60 miles apart. So it's really physically possible to do this trick of like moving two particles that are entangled really far apart but maintaining their entanglement. Okay, so what is this cool teleportation experiment that you can do? Now don't get too excited. This is not about physically teleporting matter, as we'll see. The thing that gets teleported is information or a quantum state, but you call it teleportation and it sounds cool. Okay, so what is the story behind quantum teleportation? And I should add that it's not just a party trick. As I'll mention at the end, like there's some reason why you would actually maybe want to do this teleportation if you're trying to build like a little quantum computer. But I'll just tell it in story form first. So let's imagine that like Bob is back at his lab. And then like his boss, whose name is Charlie, because that starts with a C, comes in and hands Bob a new qubit. Bob, which we'll call C, which maybe Charlie made themselves. And Charlie, commands Bob, like, please, Bob, transfer the state of this qubit to Alice. Now notice I said transfer the state of this qubit. He's not necessarily telling Bob, get this physical object that is this qubit over to Alice. He just wants Alice to have a qubit that's in the same state as C. So let's say that Charlie made C in this state, it's just one qubit. We'll just say X amplitude on 0 and Y amplitude on 1. Okay? So Charlie wants Alice to hold a qubit that's in this state. That's the task. Now, what are Bob's options? Okay, one option Bob has is he could just like walk over to like CMU from Pitt and like just hand C over to Alice, and he's like, here you go. But he doesn't want to do that. It takes up effort. Now, another thing you could consider is, what if Bob knew X and Y? In this story, like Bob actually doesn't know what X and Y are. Like Charlie just came over and said, like, here's the qubit, do your job. But suppose, I don't know, maybe Bob knew it. Like maybe Charlie told Bob X and Y. Then Charlie wouldn't himself have to like physically walk over to Alice. He could like call her or text her. He could just text her X and Y. And he could say like, yo Alice, please make a state with X amplitude on get 0 and y amplitude on 1. And Alice would say, like, okay, no problem. In fact, Alice could then make 50 states in this, 50 qubits in this state, because she knows x and y. She could make as many copies as she wants. There is actually a little slight hitch with that. It sounds cool, but actually x and y are like arbitrary real numbers. Well, their squares have to add up to 1, but I don't know, x could be like 0.123426945, etc. So if Bob wanted to literally get Alice to have the exact state, he would have to like text her like infinitely many digits of precision of x. Now, practically speaking, like, okay, I'm sure like you don't need more than like 100 digits, but so maybe you'd only have to text her like 100 bits of information. So this is like only a minor issue, but you know, in theory, like even if he knew x and y, it would be hard for him to like literally perfectly get the state to Alice. But in this story, we're going to assume that Bob doesn't know x and y. Because like in the story I told, like Charlie just came in to Bob's office and said, here's the qubit, please teleport its state to Alice. And we saw a while ago when we were studying like learning mystery rotations and distinguishing qubits, this like no learning principle, which says that if you just get like one copy of like a qubit in an unknown state, there's basically nothing you can do to like learn the amplitudes x and y. You can hardly get any information at all. So Bob cannot even try this strategy of trying to figure out x and y and then just like sending x and y in a text message to Alice. But we'll see, this is the point of the teleportation, that assuming like sometime beforehand Alice and Bob did this, they shared an EPR pair, they like got together physically, ran this code, made 2 qubits in this joint state called A and B, and then they went to their separate offices. Assuming they can do that, they have done that, then they can like, Bob can perfectly accomplish Charlie's wish. Okay, and that's teleportation. So let's see how to do it. So first I'm going to tell you the sketch of how it looks, and then we'll do the details of how it looks after that. So let's start with the sketch. Okay, so step 0, it's not really a step, but they like are supposed to have pre-shared an EPR pair. Okay, then we assume they did that like the previous day. Okay, so now let's look at it from Bob's point of view. He's the one that got the command. Bob is now holding on to 2 qubits. He's got B, that's the half of the EPR pair, and he's got C, that's the qubit that like Charlie just gave him. So what can Bob do? Well, he can do some operations on B and C. So, okay, that's what he'll do. So Bob does some, qubit manipulation operations on B and C. Okay, now, at the end of the story, Alice is going to be holding on to a qubit in this state. And we kind of know that the EPR pair must somehow get ruined or deleted. Because if it didn't, if like Alice could just get a hold of this qubit in this state, but Alice and Bob still have their EPR pair, then, well, I should say that, okay, maybe like the 2 qubits B and C have to somehow get ruined. Because if at the end of the operation, Bob still held on to B and C, and then Alice had a qubit that was in this state, then it would have been like we cloned this state. We would have gotten a copy of it. And if like this wasn't disturbed, we could just like repeat this operation over and over, and Alice could get as many copies of this state as she wanted. And that, is in contradiction to like the no learning or no cloning principle. So kind of like B and C have to get ruined by the end of this operation, or deleted. And indeed, the next thing that Bob is going to do is delete them by doing an extraction operation. So Bob will do extract B and C. Okay? And he'll see 2 bits on his measuring device's output. Which I'll call little b and little c. Okay, so these are normal classical zeros and ones, the readout of his measurement device. And as a side note, at this point, the only qubit that still exists is A, Alice's qubit A. And as I can say, as a side note, at this point, A is almost in the correct state. Okay, when we do the details, we'll see what is meant by this, but it's practically correct. Okay, then Bob will send a text message to Alice, which just contains these 2 bits of information, B and C, his measurement outcomes. So in this whole story, Bob does send Alice a message, but it's just 2 bits, B and C. And then finally, Alice, using this information, this little bit of information that she got from Bob, does some operations to A to fix it up to the desired state, x amplitude on 0 and y amplitude on 1. Okay. So I'll fill in the details here, which is basically, the only details really are what operations Bob does in line 1. And then line 4, what it really means is there's 4 things that Alice could see. Bob could text either 00, 01, 10, or 11. And in each of these 4 cases, Alice does a different operation to A, and then she's done. So I have to also tell you, what are the 4 different things Alice might do, depending on the 4 messages she might get from Bob. Okay, but before we do that, let me make some comments about this. So one thing is, afterwards, the only qubit left is A. Okay, B and C get extracted and therefore deleted. And in particular, C itself is gone. So it's not like, Bob and Charlie together maintain a qubit in this state, x0 plus y1, and also Alice gets a copy of that state, because we know this is impossible from the no cloning or no learning principle. And also their EPR pair is ruined, so if they want to do another teleportation, they have to have done another pre-step 0 where they shared another EPR pair. It's also important to note that Bob only texts 2 bits. Yeah, at the end, Alice's state's going to be literally exactly correct. So this is even way fewer bits than Bob would text, even if he somehow knew x and y. Even if he knew x and y, he would have to text Alice all the digits of precision of x, and maybe also the sign of y. But here he only texts 2 bits, so that's pretty cool. Another thing to note is that no physical qubit gets teleported or moved. Okay, so despite the exciting name, it's not like a physical electron warps from Alice's office, Bob's office to Alice's office. Just some states get changed. But actually, some physical object does move from Bob's office to Alice's office. Can you see why? Yeah? Yeah, I mean, when Bob communicates two bits of information to Alice, some physical object has to do that communication. I don't know, it's some electrical signal, or I guess it goes into a satellite. But, some physical stuff does move, but it's only carrying 2 bits of classical information. And the other thing to observe is, actually neither Bob nor Alice ever learns X and Y. So Bob accomplished this despite not knowing what X and Y are. Also at the end, he still doesn't know what X and Y are. Also at the end, Alice also doesn't know what X and Y are. She just knows, like, okay, cool, I've got this state that's exactly the state that C was in at the beginning of the story. Okay, so before we do the details, any question? Oh, I should pass out this. Yeah, this whole teleportation story is just to make like the code exciting. I'm going to show you like 4 lines of code with 3 qubits involved. And if I just shown you that code, you'd be like, this is kind of boring. But this makes it exciting. And the fact that you can genuinely do this, and they've done this, where like Bob and Charlie are on Tenerife and Alice is on the other one, or Alice and Bob are in a base in Tibet, and Bob and Charlie, and Alice is in a satellite. That's pretty cool. It's so funny, for the satellite one, their physical instantiation of qubits were photons, like particles of light. And they're like, in the paper about it, they're like, we could only try this experiment like once a month, so it took a really long time. And you're like, why could you only do it once a month? And they're like, we could only do it once a month because we have to only do it on nights that had a new moon. Because if there's any moonlight, like the light coming off the moon would like bounce onto like this photon that we're trying to, in this step, when they've made the EPR pair back on Earth and then want to get like Bob's qubit like up to the satellite, they have to like literally shoot the photon up there, and like if some stray moonlight hit it, it like screws up the entanglement. So yeah, physics, it's actual physical things.